Right. So we are in the last part of the discussion about finite wavelength effects. So we are going to discuss about the product quantization errors. So what are these product quantization errors and how do they are said to be minimized? So product quantization errors. So this is somewhat similar to the input quantization error that we have seen, or the quantization error due to the inputs that we have seen in the earlier videos. So here in the realization, I told you we use three important parameters. So one is multiplier, another one is an adder, and then we have the delay element. So here the concentration is on the product quantization with respect to the product. So that means we restrict our discussion, or we concentrate on the multiplier part of the realization structure, right? So the output from the multiplier will be obviously stored in the register, so which is of course of a finite duration length. So if your product that has been obtained after multiplying so exceeds the length of the register, it is obviously has to be quantized. So because of that quantization, you have the error that is being observed, which is called as product quantization error. So the product quantization error, as in case of input quantization, so always follows the quantization with respect to rounding rather than that of the truncation. So the reason we have already seen with respect to the input quantization, the same even applies here also. So again, I'm repeating, the reason is that the mean value will be 0 and the variance will be minimum when with respect to the rounding of quantization when compared to the truncation. So hence we follow the rounding process for minimizing, for studying the quantization concept with respect to the product quantization, right? So here, so I'm going to give you some overview of this concept. So here also we have the term called as noise transfer function. So in short, we represent it as NTF, noise transfer function. So this noise transfer function is a transfer function from the noise source to the filter output. Right? So this is transfer function from noise source to filter output. So this is called noise transfer function, right? So here the noise term, or the signal that you are obtaining, getting from the noise source itself, will be considered to be the actual signal rather than the input that you are giving. So the signal that has been produced due to the noise source will be considered as the actual input. That is the major consideration here. So graphically, if I represent, so my input is x of n. So I have multiplied my input function by a constant a, so which produces a into x of n. So this is what I have to treat as my original output, but unfortunately we have a error that is being added here, which is e of n, right? So the output obviously will be the quantizer part of this, q of a into x of n, which is equal to a into x of n plus e of n. So this will be the output that we observe at the at this point, right? So where a into x of n represents your unquantized function, and q of a into x of n is the quantized function. Right? So where the quantization is the product quantization. So a is your constant, you are multiplying that constant with your input function x of n. So you are taking the product of these two terms. So it is quantized and hence it is product quantization, right? So this is how we generally give the equation for the product quantization. So this product quantization can be represented with respect to the direct form realization structure as well as the cascade form realization structure. This will see only the representation. We are not going to derive any expression or solve any problem using this, but rather we just will have a look how we can represent the product quantization using this direct form structure as well as the cascade structure. Right. So this is the direct form structure. Right. In this structure, you can see you have three product elements. So three constants. Right. So one is A1, B0, and B1. So three product elements we have, and with reference to these three product elements, we have three error functions being observed. So this function is with respect to A1 product A1 constant. So this is with respect to B1 and this is with respect to B0. So three errors we have in this case, right? So this is the direct form structure of representation of the product quantization error, right? So we will see in the same way the cascade quantization. Okay, so now the second form, that is the cascade form of representation. So in cascade form of representation, we consider the transfer function is said to be divided into two parts as two single transfer functions of order 1. So even the previous case what we have seen is the first order direct form structure. Now here also we are going to look at the first order functionalities. Okay. So this is x of n. This is the error function. So this is B11. Here, because of this, you have the error function. This is added here. EB11 of n. Right? On the other hand, so I'm continuing here. Mm. So here is the delay. So let me say this is A11, this is A12. Then I have the error function here. So this is E A12 of n, and here again I have B12, and with respect to this product I have EB12 of n, and this is, I don't know. So this will be my final output y of n, right? So these are the two transfer functions which are combined together. So in order to form the cascade structure, as place is not sufficient, I have continued it here. So here you can see with respect to this particular structure, you have A11 and B11, two product functions. And with reference to these two product functions, you have two error functions correspondingly. EA11 of n, EB11 of n. Similarly, for the second transfer function, which is of order 1, both the transfer functions are of first order only. Okay, so this is A12 and this is B12, and correspondingly you have EA12 of n, EB12 of n. Okay, so now just the brief analysis of this mathematically. So the output noise power due to each source has to be computed separately. So we have seen, we are considering for the cascade case rather than that of the direct form case. Even this we have seen in the input quantization, that cascade form will produce less variance when compared to the direct form. And even in the second part, that is coefficient quantization, we have seen your coefficients will be nearer to the original values when you consider the cascade structure of realization. So even here for the product quantization also, hence we can have a conclusion that the cascade structure will give you somewhat appropriate or accurate results compared to other form of realization structures, right? So here we are considering again individually you have to compute the variance for the transfer functions, and then you have to add the individual transfer function, individual variances, so as to get the total variance. Okay, so for structure 1, let us say if h1 is the first transfer function, h1 of z represents your first transfer function for your first cascade structure, you have to calculate the variance for this h1 of z, and if h2 of z is the second transfer function, let us say sigma eo1, right? So the second transfer function is h2 of z, and corresponding variance is sigma eo2, right? Then your total variance will be sum of these two variances, individual variances. Okay, so this is how we calculate the total output variance, sigma EO or EOP, let us say output variance, sigma EO1 square plus sigma EO2 square. So this is how we calculate the output variance. So before going to calculate the output variance, we have to calculate obviously the input variance, which is given as q square by 12, right? We have already calculated, or we have already seen that in case of the input quantization. The same process we follow even here also. Okay. So the input quantization, input variance of kth noise source, or the variance with respect to input, sigma E square is equal to q square by 12, and the mean is obviously mean is equal to 0. This we have already proved in the previous case. Now even here we have to calculate, as I have told you, the output variance. So output variance EOP square equal to sigma E square into sigma n runs from 0 to infinity h of n square. The same equation as we have seen in the previous case. So if we are calculating for the kth period, so we just go with k. Otherwise, if it is generalized, I don't consider even k. I directly write it as sigma EOP square is equal to sigma E square plus n runs from 0 to infinity h of n whole square. Right? Now using the Parshall's condition, so this can be given as sigma E square into 1 by 2 pi j, the contour integration of T of z, T of z inverse dz. Right? So this is from Parshall's identity. So just you can recall the properties of DFT that we have discussed in our second unit. There I have given you the Parshall's identity. From that Parshall's identity, we are writing this equation, and this is of course a contour integral. So where the contour integral defines that the poles has to lie inside the unit circle, or you will be considering to realize the structure only those poles which lie inside the unit circle. We neglect the poles which are outside the unit circle, right? So this is equal to sigma E square into, so applying the residue theorem, sigma I runs from 1 to n T of z into z inverse. So at z is equal to pi. Right? Now sigma E square, sigma I runs from 1 to n z minus pi into T of z inverse to z inverse at z equal to pi. So sigma UOP square. So this is the output variance or noise power. Output noise power or output variance is given with this formula as sigma E square I runs from 1 to n z minus pi tz inverse into z inverse at z equal to ti. Right? So always you have to remember when you are considering this part. So with respect to the contour integral, it is to be underlined, an underlined point that the poles which lie inside the unit circle only will be considered in order to apply the quantization principles or in order to realize the structure. So that is what we have to make a note of that. Okay, so this is briefly about product quantization. So example I have given in the notes, you can just go through the example. So if you have any doubt in the discussion period, we will be discussing once again about this product quantization error. Okay, so the last topic of the unit and of your DSP syllabus, that is limit cycles. Right, now what are these limit cycles? The name itself says it is a cycle, so that means it will have some oscillations. So these oscillations occur due to the arithmetic operations on these linear, the so-called linear systems that we consider in realization of the DSP hardware systems. Either it could be IIR filter or FIR filters. So these basically these limit cycle operations will be observed. I've told you even when we are discussing the differences between FIR filters and IIR filters, limit cycles will be observed in the IIR filters only. We don't observe limit cycle operations or oscillations in the FIR filters. So they do have the impact only on the recursive systems, not on the non-recursive systems. IIR filters are recursive systems, whereas FIR filters, even though they can be implemented as a non-recursive or non-recursive systems, as they don't have the concept of feedback, So they will generally be considered as non-recursive systems. So in the recursive systems, so when the input is 0 or some constant value, so you will have non-linearities due to finite precision arithmetic operations. So because of these non-linearities, we will be observing the oscillations in the input and output parts of the system, right? So these oscillations are said to be called as limit cycle oscillations. I'm repeating, so try to understand carefully. So in the recursive system, so when the input is 0, that means you have not applied any input, or there is some constant input being applied. So due to the impact of this quantization effects, so you will have non-linearity being observed on the system performance. And because of this non-linearity, you will have oscillations in the output of the system. So these oscillations are called limit cycle oscillations. Okay, so they range from positive value to some negative value, and again they jump back to some the positive value. So like that, you'll have ups and downs, crests and troughs, right? So these recursive systems continue to remain in the same limit cycle or the oscillation process, even though you apply some input or you don't apply any input. So once the system has entered into this limit cycle, refers that the system continues to follow the same limit cycle operations, or they will be exhibiting the same oscillations. So now how to control these oscillations? You have to give an input or a push to the system which is somewhat equivalent to the oscillations that are being produced, right? So until and unless another input is said to be applied to the system with sufficient magnitude to control these limit cycles, your limit cycles will go on, your system will go on operating with these limit cycle oscillations, even though you make your input equal to 0, right? So that is the concept of limit cycles. So in limit cycles, generally we have two categories. So one, they are called as zero input limit cycles, and the second one, they are called as overflow oscillations. So we have two categories as zero input limit cycles. The other case is overflow oscillations. As I have told you, so once the system has entered into limit cycle operations, and when you even make your input 0, so you are making your input 0. So hence they are called zero input, right? So even though you have made your input 0, the limit cycle oscillation still continues. So hence they are called zero input limit cycles. On the other hand, these are overflow oscillations. So basically these are with respect to the multiplication that we observe, and these are with respect to the additions that we perform. So in overflow oscillations, so this is due to, as I've told you, these are due to additions which make your output to oscillate between maximum value and a minimum value, right? So that means maximum amplitude to minimum amplitude, your signal will be varying. Now, why do these overflow oscillations occur? So when you have two values, binary values that are to be added, right? The sum that you have taken has exceeded your register length. Okay, so initially you have a register of a particular length into which you have to store the output of the two digits that you have added. But unfortunately, the sum that you have obtained has exceeded the length of your register, right? So such case where you cannot fit the output that you have obtained into the register that you have, overflow oscillations, right? So this is about limit cycle oscillations and overflow, in which you have zero input oscillations and overflow oscillations, right? So a small example we will take to conclude this session. Okay, so here one more important point that we have to observe is the dead bands. Right. Now, what are these dead bands? As I have told you, when we are going with these limit cycle oscillations with respect to either zero input limit cycle or the overflow limit cycles, so there will be a maximum value of amplitude and the minimum value of amplitude. Right. So your oscillations will be between a maximum value and a minimum value. So these maximum and minimum value of the amplitudes in the output are confined to a particular range of values, right? So the amplitude values of the output are confined to a particular range. And this range is called a dead band, right? So the range of values over which your amplitude oscillates from a maximum value to minimum value with reference to the output that you have obtained after doing a particular process by using the recursive filters. So that is called dead band. So here the dead bands in general are given as dead bands is equal to 2 to the power of minus b by 1 minus mod a. Right? So as it is range, we take it plus or minus. So that means minus 2 to the power of minus b by 1 minus mod a 2 plus 2 to the power of minus b by 1 minus mod a. Right? Now where does this mod a come from? So we know what is b. So b refers to the bit representation including the sign bit, and the mod a come from your general equation of order 1 I am considering here, a y n minus 1 plus x of n. So if this is the equation that we have, so this product, the coefficient term with respect to your first delay element yn minus 1 refers here. So from this point I have got my a value, right? So these are the dead band effects. Now let us take an example to observe how these limit cycle oscillations impact your filter performance. Okay. So consider an example y of n equal to 0.95 y n minus 1 plus x of n. So here he is saying the product is quantized by 5 bits. He is saying that the product is quantized by 5 bits, and he is obviously applying the concept of rounding. As I told you, rounding gives you a more accurate result compared to the truncation, right? And the system is excited by the input x of n is equal to 0.75 when n equal to 0, and it is 0 when n is not equal to 0. So at 0 interval you have some input in order to excite the system, and remaining all you have the 0 value of the input. Now for this system we see how the limit cycle oscillations, the characteristics of limit cycle oscillations, and where exactly the dead band range is, right? So let us say y dash of n is your response after quantizing your product. So q of 0.95 y n minus 1 plus x of n. Right? After quantization, your output is like this. Now let us say we consider case by case. Let y dash of n is equal to 0 for n less than 0. Right? So therefore, when n equal to minus 1, so when n equal to minus 1, what happens to this? So your y dash of n equal to y of minus 1, which is obviously equal to 0. For n less than 1, we have considered it as 0, so it is 0. Now for n equal to 0, your y dash of n is equal to y dash of 0 is equal to q 0.95 y minus 1, right? So y dash of minus 1 plus x of 0. We are considering n equal to 0. So here we have considered n equal to minus 1. So when it is minus 1, n equal to minus 1 minus 1. Right? So y of minus 1 equal to 0.95, y dash of minus 2 plus x of minus 1. So for n not equal to 0, this is 0. And as we have considered even this as 0 for n less than 0, so the entire term will become 0. Okay. Now when n equal to 0, we have this factor. So here, so q of this value is 0 plus 0.75. So let me write it at the top. So this is equal to q of 0 plus 0.75, right? So this is equal to 0.75, which is to the base 10. Now if I convert it into the binary, 0.1100 to the base 2. Now the second case, when n equal to 1, let us say n equal to 1. Now your y dash of n equal to y dash of 1 equal to 0.95 y dash of 0 plus x of 1. So for n greater than n not equal to 0, it is 0. So your x of 1 is 0. So this is equal to q of 0.95 into 0.75. Right? So this is equal to q of 0.7125. Now convert it into binary and quantize it to 5 bits. So what you will get 0.10110 to the base 2. Right? Converting into binary and quantize it to 5 bits. Okay. So this is the result that we have obtained. Now the next case. Now round it off to the 4 bits. So 0.10110 to the base 2. Now if I round it off, now 0.1011 to the base 2. This is equal to 0.6875 to the base 10. Right? So this is when n equal to 1. Now if I say the next value n equal to 2. When n equal to 2, y dash of n is equal to y dash of 2 is equal to q of 0.95 y dash of 1 plus x of 2. So again this is 0. So this is equal to q of 0.95 into 0.6875. Right? So the product is q of 0.653125. Right? Now 0.653125. If I convert it into binary, so this will be 0.10100 to the base 2. Then adding a sign bit to it, 0.10100 to the base 2. Right? Convert to binary, then add sign bit. Okay. Now round to 4 bits. So if I round to 4 bits, this will be 0.1010 to the base 2. Okay. So 0.1010 to the base 2. Now from this, you extract the sign bit. So by extracting the sign bit, this will be 0.1010 to the base 2. Now you convert it into decimal. So the same will be applied even for the n equal to 1 case also. So if you convert it into decimal, this will be 0.625 to the base 10. Okay. So first I am considering the original value. So for quantization, I am converting it into the binary, adding the sign bit. After adding the sign bit, I am rounding it off to the 4 bits. After rounding off to the 4 bits, I am again extracting the sign bit back, and then I am converting again into the decimal value. Right? So this is how we obtain the result. So now quantization of this value, what you have obtained, it is 0.625 to the base 10. Right? The next case, if I say n equal to 3, if I say n equal to 3, so y dash of 3, which is equal to into 2, so this is 0.625. So x of 3 is obviously 0. Okay. Now taking the product of these two, 0.95 to 0.625, you arrive at 0.59375. Right? Now apply the same method here. So 0.59375, convert it into binary. So first convert it into binary. So now if I convert into binary, it will be 0.10011 to the base 2. Now add the sign bit. So this is 0.10011 to the base 2. Add sign bit. Right? Now after adding sign bit, round off to 4 bits. So we are rounding off to the 4 bits. So the last digit is 1. In the previous case, last digit is 0. So in this case, the last digit is 1. So we will be adding 1. So it results 0.1010 to the base 2. Right? Now again, if I extract the sign bit back, extract the sign bit. So this will be 0.1010 to the base 2. And if I convert it into decimal, so this will become 0.625. So your original value is 0.59375. But after quantization, the value you have obtained is 0.625 to the base 10. Right? So y dash of 3 is 0.625. So if you observe carefully, your y dash of minus 1 is 0. Your y dash of 0 is 0.95. Right? It's a 0.7. Now 0.75. Your y dash of 1 is equal to 0.6875. Your y dash of 2 is 0.625. Your y dash of 3 is 0.625. And if you go on calculating in the same way, even your y dash of 4 will also be 0.625. Y dash of 5 will also be 0.625, and so on. So this continues. So that means at n equal to 2, your system has set to be entered into the limit cycle oscillation path. Okay. So the characteristics that we have observed here and the conclusion that we can make here is at n equal to 2, the system enters the limit cycle oscillations. Okay. Now let us calculate the range, that is the dead band. So the conclusion that we can make, as I have told you, system enters into a limit cycle at n equal to 2. Now what are these dead bands? How do we have to give the range of these dead bands. So I have told you dead band equal to plus or minus 2 to the power of b by 1 minus mod a. So 2 to the power of minus b by 1 minus mod a. So that means this is minus 2 to the power of minus b by 1 minus mod a to plus 2 to the power of minus b by 1 minus mod a. What is the value of b? It is given in the question that b value is 5. Okay, so now you may get it out. When b value is 5, why did we take in the previous calculations as 4 values after your point? So when we have represented your binary, we have rounded to 4 bits. So but the value is given as 5. So this 5 includes magnitude. Okay, so we are rounding only with respect to the this includes your sign bit. We are rounding only with respect to the magnitude. So hence we have considered only rounding off to the 4 digits there, not the 5. Okay, so b value is 5 and your a value from the question it is 0.95. So if I substitute minus 2 to the power of minus 5 by 1 minus 0.95 to plus 2 to the power of minus 5 by 1 minus 0.95, right? So it results as minus 0.625 to plus 0.625. So that means you can observe here even the limit cycle oscillations that you have obtained is the same value 0.625, right? So this is how we calculate the dead band for the given system. Okay, hope you understood what is this limit cycle oscillations, what are the types of limit cycle oscillations. So briefly they are called as zero input limit cycles and overflow oscillations. So these zero input limit cycles are also called as granular noise. Try to remember the point. So you may be asked a question to explain about granular noise. Don't get confused. It is nothing other than refers to the zero input limit cycle. Okay. So zero input limit cycle and overflow oscillations. So this is the conclusion of the topic and the conclusion of unit 5 and the conclusion of your DSP syllabus. So please refer the textbooks and practice as many as number of problems that are possible. So I also will try to share some of the previous question papers through the Google Classroom. So you can practice even those questions also. If time permits, we will work out on those problems even in the class once the college reopens after this curfew process and all. So we'll be meeting in the discussion tomorrow by 9 AM. Right? So thank you.